presented by Caltech.
It's my distinct privilege to introduce our speaker this evening, Dr. William L. Johnson, the Ruben and Donna Mettler Professor of Engineering and Applied Science. Professor Johnson received his bachelor's degree from Hamilton College, Ohio. He came to Caltech to pursue his graduate studies and received his PhD in applied physics in 1975, based on his work on superconductivity of metal semiconductor alloys. After graduation, he spent 2 years at the IBM Thomas J. Watson Research Center and was invited to join Caltech faculty in material science in 1977. He was named the Mettler Professor in 1989. He has held visiting professor appointments at the Metal Physics Institute in Göttingen, Germany. Professor Johnson's research is focused on processing and properties of metallic materials, including liquid alloys, bulk metallic glasses, nanostructured metals, and metal matrix composites. His ability to combine deep theoretical understanding with outstanding experimental skills has made him the undisputed leader in processing and properties of metallic glasses. He is widely considered to be the father of bulk metallic glasses, which are a new class of structural materials with unique and unprecedented properties. Professor Johnson was instrumental in translating the research from his laboratory into real-world applications for these novel materials. He is named an inventor on more than 100 patents and is the founder of 2 companies. He has been championing the use of metallic glasses as structural materials in sporting goods, consumer electronics, aircraft, and defense hardware. Professor Johnson has received numerous awards and honors, which include the Hume Rothery Award from the Metal Society and the Gold Medal from the Materials Research Society. He is the recipient of an Alexander von Humboldt Foundation Distinguished Scientist Fellowship Award from Germany. He is a member of the National Academy of Engineering and the National Academy of Sciences. He was most recently elected to the National Academy of Inventors. Ladies and gentlemen, please join me in welcoming today's speaker for the Watson Lecture, Professor Bill Johnson.
So, thank you, Ravi, for that kind introduction, and thank the Watson Committee for giving me the opportunity to talk about something that's preoccupied my interest for the past 4 decades. Okay. I've given 3 Watson lectures. The last one was in 1994, so this in some respects is kind of an update. The first one was in 1979. So my title is What Are Glasses? And if you come away with a few things from my talk, I want you to understand what a glass is and understand what a metallic glass is and where you might see one on the street. Okay, so what's a glass? Well, when I use the term glass, most people think of that. That's a Nestoric piece that I bought in Cambria. It's studio art glass. And that's leaded glass. Nobody likes lead these days, but leaded glass is still wonderful. Actually, I was given this by University of Michigan about 2 months ago, and I like it, so I thought it's a good. That's glass. Silicate glasses, windows, glassware, art. Polymers and plastics are glasses. There are molecular glasses like glycerol, soap. Plexiglass, metallic glass, and say what? Most people ask me if you can see through it. What makes something a glass is where the atoms are at. It's got the atomic structure of a liquid. What makes something a metal or a semiconductor or an insulator is what the electrons are doing. And so we have a material here that's glassy from an atomic point of view, but the electrons are free to roam, so it conducts electricity and looks like a metal. Okay? I'll show you pictures. So, give you a better idea, almost every metal or metallic object that you've ever encountered in the real world has a crystal structure that either looks like that, that's called face-centered cubic, that's the structure of copper and nickel and stainless steel. The atoms are arranged like that. And what you see is they're periodic, they have patterns. If you know where one atom's at, you know where they're all at. All you have to do is translate along and it's all pretty happy, everybody looks like that. A liquid, if you melt copper, well, it's kind of a mess. We'll look at a picture in a minute, but if you take copper and mix it with titanium or zirconium, you can make a glass, and that's a molecular dynamics simulation done by a former student of mine who's a professor at Johns Hopkins, and that's a picture of copper zirconium metallic glass. And you see, this looks like a kind of jumbled up mess. It's a liquid that's frozen. And if you look at what's going on in any particular location, there's just all kinds of local neighborhoods. Some places you've got icosahedra, they have five-fold symmetry. When you have a crystal, five-fold symmetry is not allowed. That doesn't fill space. Crystals have three-fold, four-fold, and six-fold symmetry. Liquids locally have icosahedra, right? So they're different structurally and no long-range order. So that's where sort of what the atoms look like. So the question next is, how do you get from here to here? Okay? If you cool a liquid down, when the liquid's at high temperature above the melting point, it sort of looks like this. Every atom's got a little bit different neighborhood. Some atoms are squeezed together by their neighbors. It's like a crowded mess on a city street. And it's sort of like society. How the heck are we going to get organized, right? To get from a liquid to here is actually an extremely interesting exercise. Now, when you cool a liquid down, things vibrate slower. It shrinks a little bit, thermal contraction with cooling, and everything gets a little more crowded, and it's like you in a crowded room with standing room only. When the density of people gets too high, you just can't move anymore, right? We freeze. And when you freeze the liquid, you got a glass. So as you cool it down, either you get to here or you get stuck here, all right? And so how does this happen? Well, the talk's not too technical. It all starts with nucleation. Nucleation is an interesting concept. If you're trying to solve a problem, you have all kinds of ideas, and then one day you wake up, there's that eureka moment, and you say, oh, I understand it now. I just didn't have to see it the right way. You nucleated an idea, right? Or you post a video on YouTube, and you get some views, and sometimes you get a few views, and then you get a few more views, and then if the mood is right, it goes viral, right? So there are these fluctuations in that random liquid mess, and crystals try to form. If they're too small, they're fighting against their neighbors that are in the wrong place. As you get more and more of them together and making a bigger crystal, they win the battle against their neighbors. They call that the nucleation barrier. And if you get over that nucleation barrier, if the nucleus of atoms gets to a critical size, then it takes off and it grows like crazy. Once it gets critical, it grows. So when we want to make a glass, we have to stop that critical formation of a nucleus that will grow. And it's actually wonderfully exciting to see what it looks like. Now, just as in the way of explanation, I'm going to show you an infrared movie. And the movie's actually a liquid sample. It's in a cylindrical form. It's contained on a quartz tube. And we've got an infrared video camera which sees temperature. And when a crystal forms, things get organized, they lose some energy, they fall into a potential energy well, and all that energy that's lost is given up as heat. So when a crystal forms, it gets hot. So if we watched a liquid that was cool below the melting point, a crystal forming somewhere would correspond to a sudden release of heat at a point. And once it reaches that critical size and takes off and goes viral, it's going to grow like crazy. And so I'll play the movie. This is an infrared camera, so the camera sees, what we're going to do is we have a liquid at low temperature, and I'm going to heat it up very fast. We'll talk later about how we heat it up really fast. We heat it up at 100,000 degrees per second, and we get to some temperature and sit there, and we watch the nucleation process. And the crystals form somewhere, and then they grow, and you can see it because it lights up. So let's play the video. Okay, that's fast, that's real time. And now I'm going to play it at 100 speed, and these are thousandths of a second. So it's a very fast infrared camera, and there a crystal formed. And this is about an inch. And in a few hundredths of a second, the crystals grow all the way across the sample. Once it goes viral, it goes like crazy. You can actually figure out it's going 2 meters per second. That's a little faster than you can walk. It's also enormous when you think about how big atoms are. This crystal forms, and then it's going to grow. And it grows by adding atomic planes, and it's going to add 10 billion atomic planes per second. So once the crystal's stable, it just, pew, right? And it's all over in a flash. So if you take a piece of copper and you cool it down, at some point you're going to form a crystal, and then it's going to solidify by releasing all this heat, and it's going to shoot through the sample. That's how. Now, if we're going to make a glass, we have to avoid the nucleation event, the local embryo that triggers this. And so, just a little bit about the science. The first person who really worried about this problem in metals was a fellow named David Turnbull, who was working at GE in Schenectady, New York in 1949. I guess I was 2. So he developed a theory for how these nuclei form. And I'm not going to get into all the details, but a glass is the liquid that freezes without crystallizing. That's where the metallic glass definition came from, and we have to avoid nucleation of crystals. Turnbull concluded, after 3 or 4 years of working on this problem, that any liquid, including a metal, would form a glass if you cooled it fast enough. In other words, these formation of embryos takes time, and if you can cool the liquid down and freeze it, solidify it, set it up, vitrify it, those are the terms we use for glass blowing and all that. If the liquid freezes, then no crystal is formed, and we got a glass. So Turnbull said metal crystals grow very fast. I just showed you how fast. And the atoms rearrange themselves it's very fluid. And so crystals form very fast, then metals don't exist, metallic glasses don't exist in nature, because normally in nature we can't cool something fast enough to make a glass. So my advisor here at Caltech, okay, let me sort of depict what I'm talking about. Here's a liquid, that's the melting point. So the liquid is stable up here. It's the equilibrium state. That's like the melting point of ice. And If we cool the liquid down far enough, it sets up and vitrifies, becomes solid. That's a glass, right? And that's called the glass transition, where it sets up. And we have to get from here to here before we get to there. And that's the time it takes for a crystal to form in a cubic centimeter or some volume of liquid. That's Turnbull's theory in a picture. And there's some temperature down here in the liquid cooled below the melting point, but still above the glass transition where that crystallization rate is maximum. And we have to cool fast enough so we don't hit this on the way down. That's schematically what we have to do. If we can do that, we make a glass. Well, it was previously thought that metals don't make glass, but my advisor back in the 1950s, Paul DeWay, he's shown here with Theodore von Karman, who was a pioneer in aeronautics here at Caltech. He hired Paul in the 1930s. Paul was Belgian. So Paul developed something called spot quenching. He took a piston and an anvil and dropped a droplet of metal alloy and smacked it. And the anvil and piston are made out of copper. They conduct heat really fast. And he figured out that you could cool a metal at 1 million degrees per second by splatting it. It's called spot quenching. Well, he started splat quenching metal alloys and shortly discovered that some of them form glass. You cool it fast enough, there are no crystals, you get a glass. That was the first metallic glass, 1959. Okay? Rapid solidification. Paul started a whole field. It was called rapid solidification technology for processing metals at high cooling rates. Right? But he discovered metallic glass. That first metallic glass was an alloy of gold and silicon. It's a gold glass. It's like 20 karat gold, but it's glassy. Okay? The problem is you have to splat it into a foil that's about 1/10 the thickness of a hair to get the heat out fast enough to beat the crystallization, right? And so when I joined his group as a graduate student in 1971, I was trying to talk up the idea of applying metallic glass to real problems, using it for real structural applications. And Paul said that these are laboratory curiosities. Now you can quench something that fast, you make a glass. The idea stuck with me, and it took a few years, but we kept pursuing the idea of making stable metallic glasses, and this is 1991 or 2, some years later. And I had a graduate student who was trying to make metal alloys that would crystallize slower. I'll tell you how we do it in a minute, but we were cooking. We made an alloy of titanium, copper, nickel, beryllium. We put all kinds of things together. Why? Because we're trying to confuse the process of forming the crystal. If we have big atoms and small atoms, we make an alloy of many different kinds of atoms. It's harder to crystallize. Well, we got it to the point where it was so hard to crystallize that Attican came in one day and said, I melted the ingots of this, like a size of your thumb, and he let the ingots cool down, and they didn't seem to crystallize at all, and it turned out the ingots were a piece of metallic glass. So we went from the aluminum foil thick stuff, little splats, to chunks of metallic glass. This is a big chunk, and this was a very good glass former, kind of like silicate glass. It starts to look like more common glass. That's a nice ingot. We put it in the electron microscope and blow it up about 400,000 times, and you can see atoms, or you can resolve atoms, and they're all jumbled up. It's liquid-like, no crystals. If you look around, you'll see pentagons that are part of icosahedra and all that. It's a nice glass. And so the way we usually tell where the atoms are is we X-ray it, and the X-ray pattern looked like a liquid. It looks just like a liquid metal. And if you heat it up and look at how it behaves thermally, lo and behold, there's a glass transition. And you get up above the glass transition and it softens, like doing glass blowing on silicates. You go above the softening point, it gets soft, you can blow it, work it, so it softens up. And then if you keep heating it, suddenly it crystallizes. We hit the TTT, we hit the crystallization nose when we heated it up. And you take the crystallized material, you keep heating it, and it melts again, and so we made a glass. It's a big chunk of metallic glass. So, of course, when we could make these things in bulk form and at low cooling rates, Attic and Pekar was only cooling this at, go back, 1 degree per second. That was 1 million. He's only cooling at 1 degree. So we slowed the cooling from the Douai experiment down by 1 million times, and we still make glass. And we show so now how do you study these liquid metals? Well, we want to study crystallization. We want to map out that crystallization curve. We want to test the theory that Turnbull proposed. And at the time that we discovered this, I had a colleague up at JPL named Wan Q Rim. And Wan Q was involved in other things. He was trying to levitate spheres, droplets of liquid. And it was water. And he developed a technique called electrostatic levitation. What you can do with this, if you shine a laser on here and kick off some electrons, the ball gets charged, and then you can use an electric field to counteract gravity, and you can levitate the ball. You can put it in a vacuum chamber, and you can instrument it with video. You can see the crystallization event when it lights up. You can do all kinds of things. You can ping the drop and watch it oscillate and back out the viscosity of the drop. You can see how it's becoming more viscous as you cool it. You can map the freezing curve. So we can go in and look and see exactly what's going on. So with the electrostatic levitator, there's a levitated ball of the vitrified alloy, the zirconium, titanium, nickel, copper, glass forming alloy, and it's sitting here at 1300 degrees centigrade, 2000 Fahrenheit, and it's in a vacuum chamber, and there's no container, it's just hanging out by levitation. Okay? So we study this, and of course, going back here, let me, remind you this. So we melt it, we can cool it down and hold it here by adjusting the power of the laser that's using to heat it, that we're using to heat it. And we can sit here and measure how long it takes to hit this. And so we can measure the crystallization map. And there's the map of Vitrified 1. And you can see it takes 10 seconds, for example, here. That's a different alloy. This one takes 10 seconds to nucleate crystals. And we can ping the drop, make it oscillate, and if you watch the damping of the drop oscillations, that tells you what the fluidity or the viscosity is. So you can do all this stuff and measure it. It's fun to look at a movie again. So this is a levitated drop, and what we've done is heat it up above the melting point, then we turn off the laser and watch it cool down, and then it lights up when it crystallizes. So there it's hot, 1300 degrees, it's cooling down, now it's down to 600 degrees, and about 600 C, boop, there it crystallized. That's what it looks like. Crystal nucleated somewhere, grows like crazy, gives up a bunch of heat, it lights up like a light bulb. You see the drop was spinning. We can ping the drop. There you see the If you do high-speed video, you can watch the drop oscillations, you can determine the viscosity, so we can go in and measure all of the physical properties of the liquid that go into Turnbull's theory, and we can test the theory, and so on. So what do we learn? Well, we found out something that Turnbull already told us in 1949, that if you make the ratio of this glass transition temperature and the melting point of the liquid, if you make the ratio of Tg over TL high enough, you squeeze out the temperature region where crystallization can occur, and that pushes the crystallization map to much longer time, so you get a good glass. So we learned that. And we learned that the more viscous the liquid is, the slower the atoms rearrange themselves. When you're down in the middle of this region where you're at risk to crystallize, if the fluidity is low enough, the rate of forming embryos goes down, and if you freeze it far enough, you get a glass. So the two things that are competing are the ratio of this, and so we put this story together, and let me, I brushed a lot of things under the rug, but I can tell you simply what's the idea behind developing bulk metallic glasses. The materials I'll tell you about in the second part of the talk. The idea is this. This is called a eutectic alloy, and this is just a schematic diagram. We have a metal A and a metal B. They have a melting point. If we put the two metals together, they can melt at a much lower temperature. Eutectic, tektos, Greek word for liquid, U together, EU, melt together. They melt together at a much lower temperature. Well, Turnbull told us we want the melting point, we want this glass transition, which is kind of down here, to have the highest ratio as possible with the melting point. Obviously, when things melt together, you drop the melting point, the Turnbull parameter becomes favorable. The business of developing bulk metallic glasses is a business of putting 2, 3, 4, even 5 or 6 metals together to make a very deep eutectic, where we push the melting point very close to the freezing point, the glass transition, and that just squeezes the crystallization out. It works. With that idea, that's how Pekar found the first bulk metallic glass, the ingots. Well, let me show you. Once you learn more, you do your science and figure out how this viscosity story works. And I don't want to spend too much time, but when you heat a liquid up, all I want to show you here in the viscosity is that at the glass transition, the viscosity is 1 trillion Pascal seconds in that's some units. And if you have a high temperature liquid, it's 1 or 1/100th of a Pascal second. So when a liquid freezes, the viscosity, or its resistance to shear, changes by 1 trillion times as you cool it down. So this freezing is incredibly rapid. It's like the standing room only crowd. As you squeeze people together, the possibility of rearranging yourself gets frozen out very rapidly. It's called jamming. It's called a jamming transition for obvious reasons. So we play games. This is just, these are maps. And we were interested in developing practical metallic glasses that you can use. This is recent work. Now we're up to 2009, 8, right? And we wanted to, so we were exploring iron, nickel, chromium, metallic glasses. We alloyed them with things that have deep eutectics, like phosphorus and silicon, and we coax it into a very deep eutectic and squeeze out the crystallization, and we make bulk glass. except these glasses are chromium, iron, nickel. What's that? Called stainless steel. Right? That's amorphous, that's glassy stainless steel. And how did we get there? It's a long story, but basically it's the eutectic story. It's finding points in the alloy space, composition space, where the eutectic exists and the melting point's depressed to the point where, and the liquid becomes viscous enough so we can make it easy to form glass. This is how we quench little samples of metal in a tube, and as we get closer and tune it up, notice the chromium content here, that's niobium, that's boron. Notice these have a lot of detail. Why do they have so much detail? Because the eutectic point is one point in the phase diagram, and when you hit that point, the glass forming ability goes through the roof. So you get these so you tune it up and find the peaks. You find the eutectics, and there's a nickel, chromium, phosphorus, boron glass. It's kind of like stainless steel. That's a 17 millimeter rod of it. And you just heat it up, melt it, cool it in a quartz tube, use silica, because we don't want something that has crystals. That would seed the crystallization and the viral effect. So we melt it in a quartz tube, we quench it in water, and we make amorphous stainless steel. Okay, you say, oh, that's all nice. It's a great science story. Why do I care? What do I want to do with amorphous stainless steel or glassy stainless steel? Well, let's go take another look now. So that's what the stuff looks like. You can't see through it. It's a metal, but it's a glass. And that's a nice rod. It looks very shiny. It looks like a liquid because it's a frozen liquid. No crystals. You can make rods. We can process it. And so, why? Well, turns out these metallic glasses are totally different than crystals. They deform differently. They have different mechanical properties. They're very strong and they're very hard compared with conventional stainless steel. They're very elastic and springy. At one time we tried to make golf clubs. Right? Actually, John Daly and Paul Azinger used liquid metal golf clubs on the tour in 1998. Right? And they're ductile. They bend like metal, but the mechanism for deforming and bending is different. I'll show you in a second. And so we get something that's very strong, like a ceramic, but tough like a metal. And this is interesting for applications to make things out of. Okay, so just to show you, if you take a tensile bar and you pull it, these are some units, they're megapascals. That corresponds to about 400,000 pounds per square inch. So if I have a square inch bar, I could hang 400,000 pounds. I could hang 60 pickup trucks, right? That's normal metal. That's a high performance thing you make airplanes out of. It's about that strong. It's actually, I've overestimated. Aluminum's down here. We make airplanes out of that. That's steel. We make skyscrapers and bridges out of this. That's metallic glass. Okay? There's some funny things that go on. If you pull it in tension, it slides off. It forms a little bend and it just slides off like a liquid slides. What's going on here? That's very different. Well, that's what happens if you pull it. If you bend it, you see something totally different. So we take a strip or a bar and we bend it. And you see this. This doesn't look like an ordinary metal at all. We see these bands along which it shears. It looks a lot more like how nylon or Teflon crays. The deformation mechanism's totally different. The fact that you have a liquid structure changes everything, right? Let me show you how it changes everything. Well, if you're in a crystal and you want to deform it, you try to shear it by pushing the top this way and the bottom that way. Crystals form dislocations, and this is how they deform. G.I. Taylor, 1938. That's the basis of modern metallurgy, dislocations. That controls the stress that's required to make those move, those dislocations, determines the strength of steel. Now, if I take a metallic glass, this is a simulation by Marios Dimitriou, one of my postdocs who now works at our company. And if you do this on a simulation of an amorphous metal, it looks completely different. You get these, eventually things localize into bands that look like the shear bands that we saw when we were bending it. And so let me put this all together. We've got a deformation mechanism. It's very different. We've got a yield strength to get the shear bands to form that's 2-3 times higher than conventional metal. And so what's really the interesting question is, you have a very strong material. In material science, if you make something very strong, like carbon fiber, or a ceramic, or silicon carbide, it gets very brittle. Make it too strong, then it fails by cracking. And the resistance to cracking is called toughness. When we build structures or use engineering materials, what we're really looking for is an optimum balance between the strength and the toughness, right? So titanium 6-4, which you build airplanes out of, has been engineered for 30 years to be tough and strong. Tough is 250,000 pounds per square inch. Titanium metallic glass is 400,000 pounds per square inch, right? The question is, how do you trade tough and strong? And so when we try to make things, this is the world of material science on one graph if you're a structural mechanics engineer. That's strong. The scale is logarithmic, so there's 1,000 times change on this scale, and that's another 1,000 times on this scale. Now this spreads things out. So here are plastics, common things we use in the real world. There's PVC, you make your drain pipes out of that. There's nylon, and so on. Notice plastics are moderately strong, 100 MPa, 15,000 pounds per square inch. Okay, if you want to put it in practical units. But they're moderately tough, sort of commensurate with their strength. Ceramics, here's silica glass, the window pane. Man, it's strong on the strength axis, but man, is it brittle. Of course, you drop it on the floor, it shatters. You can temper it to try to stop the cracks from forming, and you do fancy things to try to make it a little tougher, but it basically, we don't build airplanes out of window pane glass. We want our airplane to fail gracefully. We want some warning. We want to go in with an ultrasonic imaging system and look for little cracks before they get big enough to propagate and the engine falls off. It actually happens. One of my Caltech colleagues was killed in Chicago in 1980 when the engine fell off of his American Airlines 727. Some of you are old enough to remember. In Chicago, we had Dick Schuster, who was the head of development here, and there were 3 Caltech people on that plane. The engine fell off, it's crack. Okay, so here's the world of metals. Metals are pretty strong. Down here, that's 150,000 psi. That's titanium and steel. That's the stuff we build airplanes and bridges out of. It's pretty strong, not as strong as ceramics. Ceramics can be 10 times stronger. Carbon fibers, for example, right? But ceramics have no toughness. You can't use them for structures. Metals have a beautiful combination. And aluminum alloys are here. They're very light. We make airplanes. Titanium alloys make some of the things in airplanes. We want to make new airplanes that are lighter and more fuel efficient and all that. And we have steel that we make skyscrapers out of. Those are here. Okay, here I took, the little X's are metallic glasses. They're at the frontier of tough and strong. They're as strong, that's the nickel, that's the amorphous stainless steel. It's out of the envelope. It's got the best combination of strength and strong and tough of anything out there. There's nothing else that is comparable. Okay? It's the best material I could think of to make things, certain things out of. It's got, the shear bands have their own problems, but okay, so that makes these materials more than a laboratory curiosity that my advisor suggested the splats were. I just want to show you, this is a crack in a piece of nickel chromium, this probably maybe a zirconium glass, and I don't know if I got, I want to show you how the crack gets arrested. You try to propagate the crack and you get these, you see these shear bands, they're all over the place. It's screening the crack and arresting the crack. That's what makes it tough. Same thing, the shear bands are the story of how it deforms, how it screens cracks, how it performs. So that's the mechanism of deformation. And just for fun, I made a little chart. It's busy, and the people who don't like technical stuff too much I just want to show you something. That's 304 stainless steel. That's a common stainless steel in the real world. Pots and pans, anything that you don't want to corrode, you make out of that, right? There's the strength of the stainless steel that we use. There's the metallic glass. There's the hardness. There's the metallic glass. This stuff won't scratch. Okay? There's the springiness, how far you can bend it before you start getting deformation. 2%, tenth or a couple tenths of a percent. That's the stuff your iPhone frame is made out of. When they make them too thin, you sit on your phone and you get a bent phone. Big problem for Apple. Right? You want to make it thinner without getting a bent phone, make it out of metallic glass. Okay? Toughness, same ballpark. We're still tough. We won't crack. So when you drop your iPhone, it doesn't break like a piece of glass. It's got to be tough. It's got to bend and not crack. So when it hits the floor on the corner, you don't want it to shatter like a piece of glass, you want it to bend. Or if you put enough stress on it to make it deform, you want it to deform gracefully. You want to put a dent in it. Okay? So just for fun, you can put it in acid and look at how it corrodes. We use stainless steel because it's very corrosion resistant. And so we put this in steel for a week. I mean, we put this in hydrochloric acid for a week, and here's the rate at which the stainless steel corrodes, and we couldn't measure anything with a metallic glass. It doesn't corrode. Right? It's wonderful. Incredibly stainless. Okay? So, I think, wow, I'm on time. Not too bad. Okay, so how would I make something out of this? Okay. Well, when you make metal stuff, airplane parts, fasteners, iPhone frames. Apple hogs the iPhone frames out of a piece of stainless steel with a computerized milling machine. That's how they make the MacBook Pro, right? They take a chunk of aluminum and they go in and they mill out all the holes, and yeah, you can machine it. You can get very precise parts that way, but it's pretty expensive. And most of the metal ends up on the floor, right? You can cast it. Casting's okay. It's got all kinds of issues, but castings, you make engine blocks out of it. If you want to make a precision part with thousandths of an inch, you don't cast it. In the modern world, a lot of the stuff you use every day is made by metal powder injection molding. What do you do there? Well, you take metal powder, you mix it with plastic powder. Plastic powder is a glass with a low glass transition temperature. You heat it up, it softens, and then it carries the metal along, and the mixture can be molded. Like you injection mold plastic parts, like Robbie the Robot, or you're the garbage can at the orchard supply. Or plastic parts are wonderfully net shape, they're precise, you can get great tolerances, and they're cheap. Why? Because we use injection molding. We make one mold, and we take the plastic and we heat it up and soften it and then squeeze it into the mold, open it up to kick out the parts, boop, 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 boop. We can mass produce parts cheap. Much easier to injection mold plastic, but much cheaper than it is to machine metal or metal powder injection mold it there. I got to blend the powders, I got to sinter it, it shrinks, I have to finish it with some machining, blah, 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 blah. Right? Well, here we have a metallic glass. Now, I told you what it has in common with plastic is it's a glass, and you saw it softens like a glass, and you can blow mold it, and technically you can injection mold it. What's the problem? That all sounds too good to be true. Well, it sort of is, because we run into the crystallization problem, and if we're molding it in the middle of the above T of the glass transition, but below the melting point where it has the viscosity that plastic has when we injection mold it, well, if we hit crystallization, zoop, it's all over. Remember, it goes viral. So, well, back to Turnbull. We've got a certain amount of time. And we got to get up here where the viscosity is like plastic, and we've got to form it and injection mold it or do whatever we're going to do and get it cooled down and not get over here. Okay? Well, that's hard to do. It's not as stable as the crystallization curve of plastic is orders of magnitude longer. Silica glass that I blow mold is the crystallization curve is 100, 1,000 times farther away. These are still not fantastic glass formers. They're good glass formers. So you got to get up here, do your forming, and get down again before you run into that. You got to go fast. So we want to take a piece of metal, one of those rods I showed you of the stainless steel. We want to heat it up. We want to heat it up in quick. We can't put it in a furnace because it takes too long to conduct the heat, and you can't go fast enough. We want to get up there and reach the temperature. We want the whole piece to be at the same temperature. Well, how do you do that? One way to do it is to pass a current through an alloy and just through a rod, and it heats up like a resistor, gives up heat. Well, if you pass enough current, you can heat fast. How much current? Well, if I have a 1/4-inch diameter rod and I pass 20 or 30,000 amps for a millisecond, I can do what I want to do. Sounds awful, right? Sounds like who in his right mind would, and let me remind you that this crystallization that's going to happen, if we take too long doing the forming, then we're going to hit that. And so what we want to do is, there's crystallization. This is time now. It's on a log scale, and that's temperature divided by the melting temperature. So the Turnbull parameter is this over the melting, and so on. This is just a little bit busier version of the TTT diagram. We want to get up here And how fast would I have to heat to get up here, do my forming, and not run into the crystal? Well, these are constant heating rate curves on the chart. So if you went at 1,000,000 degrees per second, you could get up here and you'd have a whole second to process. Okay? Well, that sounds like an awful story. These are what you can do with a current pulse with 10,000 or 20,000 or 50,000 amps, and you pulse the current. How do you do that? You take a big capacitor, store a lot of energy, and you make an RLC circuit, and you discharge the capacitor into the rod, and the time constant for the discharge should be a millisecond. That gets you up here. And then you can sit here and do your forming, and you're going to have, here you cross the glass transition, so it's softened. Now the viscosity is like plastic, and I have to get my forming done before I get here. Right? And you say, that all sounds pretty crazy. This is one of my graduate students, George Keltenbach, who now works at our company. And this is a little device we call an RDF. There's a bunch of capacitors here, and here's a rod of metal between two copper electrodes, and we're going to discharge the capacitor in 1 millisecond, take the metal from room temperature to 600 degrees centigrade, where it flows like plastic, soft plastic, like polyethylene in a molding machine. We're going to squash it. So I'm going to show you a movie that takes 13 thousandths of a second. It's pretty quick. And so what's going to happen, we applied a small force on the rod. That's a 5 millimeter rod or something. And there's about a 40-pound force. And I'm going to discharge the capacitor. It's going to get hot very fast. And you'll see what happens. It gets soft and boom, it's like putty. And these are metal surfaces, so it quenches like Dewey's old splat that's thicker, but it's cooled fast enough. We get down before we hit the crystallization. So we did plastic forming. That's molding, right? Well, you say, that looks like a laboratory curiosity. We're back to my advisor, right? And just for fun, I took the infrared camera and we ran it at 1,300 frames per second, and that's what happened. It got hot, 600 degrees, and then it got squashed. And the movie that's 10 milliseconds, it's all over. That's 100th of a second. Can I do injection molding? Yeah, if I go fast, I use capacitors, intense current pulses. And believe it or not, I started a company in 2010 with Marios Dimitriou, and we figured out how to do this and built a machine to do it. This is a rapid capacitive discharge machine. It's got a big bunch of capacitors, right? For those of you who like electronics, there's about a farad in there. We charge it to up to 200 volts so we can store 30,000 joules of energy in the capacitor, and we can deliver it to a rod of metallic glass at the bottom through copper electrodes, or we now use tungsten electrodes, and we can heat this in a millisecond to a process temperature, and we put a drive on there. That's a pneumatic drive. So there's a drive, there's a discharge, we put monitoring stuff, we can measure the force that's on the drive system, we can estimate the viscosity, we can do all the nice stuff you'd like to do while you're running a process like that. And if you put a rod of metallic glass, one of those amorphous stainless steel type rods that I showed you in an earlier picture, you can flash heat that in a millisecond. And you can put a mold here and a hydraulic clamp. That looks like a plastic injection molding machine, but there's no furnace, no hot barrel, and it's not like a Cincinnati Millicron plastic molding machine that's 30 feet long. This is, the machine's about 6 feet long, and you can sit it on a tabletop. There's no furnace. Nothing gets hot. It's all electronic. And you go boom. It gets the metallic glass rod over here gets soft. And it gets injected through a gate like a plastic injection molding machine, and lo and behold, you make parts. You make a mold, you inject it. Okay, this is a very simple mold. I just that's the barrel. There's a little gate, and I got a piece of metallic glass. It's going to get heated very fast and then squashed by the drive and extruded into here like a plastic part. And we turned that rod into that plate. And our mold was machined, not a fancy mold. It's got machine marks, and you see we replicated everything. The details of the mold, even the machine marks from milling it, are replicated on the part. It's wonderfully precise. Tolerances are 10,000ths of an inch. It's a precision metal part made out of a metal that's 5, 6, 7 times stronger than traditional stainless, more corrosion resistant, harder. So we're going to have some wonderful parts for something. Okay. So this is just showing you can put different kinds of molds. You can make little shapes and toroids and zigzags and little tier molds. That's a logo plate for our company, Glassimetal. That's our company logo. And you see the mold had little machine marks in it. Every little detail that's in the mold's picked up. That's the point. This is a screw. We made a screw mold, and we filled it up, and you can replicate a screw and get the threads and all the detail. Right? And you make a watch case. Okay? So you can make parts. And you can make them fast. You make one mold. You take metallic glass rods, and if you automate it and feed the rods in there, you can bang out watch cases or parts for your smartphone or medical instruments. So where will you see these things? Okay, what kinds of things can you do with this? Well, you can make electronic frames and casings for your iPhone or your laptop or your whatever your watch. Right? You can make dental hardware. You could do orthodontics or endodontics, make parts, dental implants, brackets, medical parts, stents, metal stuff that you don't want to be no corrosion, very springy. It's perfect stent if you're doing cardiovascular, right? You can make micromechanical devices, watches, precision instruments, gears. One of my former students is trying to put gears on the Mars rover that are made of metallic glass because right now the gears wear out and they have to lubricate them, and you have to bring a heater and the whole system along. It's a huge baggage to carry to Mars to lubricate the transmission on the rover. If you use a metallic glass, they think they can get rid of the lubrication and the heater for the lubricant and all that. Fasteners, connectors. So you could do a lot with this. That's where we're currently at. We're trying to figure out, so what's the commercial story? Well, we make precision, complex net-shaped metal parts with a very high-performance material, and we make them cheap. So if you're Tesla trying to make parts for a car, they're also very strong, so you don't need as much material to do the same job. As make it thinner, lighter, right? So that's where metallic glass is. I think these are the materials for 21st century metallurgy. And in 20 or 30 years, you'll look around, you'll see this stuff all over the place. Yeah, I think it's the engineering story is so compelling that I'm confident that this will make its way into metals manufacturing. This is advanced manufacturing for the competitiveness, all that. Yeah, this is what you do. That's not evolutionary, that's revolutionary. So I'll take questions. That's the end of my talk.